Good evening, and thank you for taking time to view my research poster. We've been researching rays and how they collect their data and what that data can tell us about the ocean and where they are located. So for my project, I chose the near polar arrays, which include the Papa Station Array, the Imaging Array, and the Southern Ocean Array. So we'll zoom in here on the poster a little bit. So first we have the abstract. Oceans are ever changing with things like varying changes in temperature, different chemical intakes and fluctuations, and changes in salinity levels of salts, to name a few. As seas continue to change, research groups like the National Science Foundation's Ocean Observatories Initiative, OOI, and the National Oceanic and Atmospheric Administration, NOAA, track the vast amount of data so we can observe and learn about these changes, as well as track and study random anomalies. They do this by setting up arrays that are placed in specific sites where 3 intelligent monitoring systems float and record data from the waters, such as temperature, current patterns, and monitoring sea creatures, and send it back to the laboratories. The research being done helps us to understand how all of the different parts mix and affect one another both positively and negatively. Here we are looking at the data from 3 different arrays known as the near polar zone clusters. As they currently monitor and have previously monitored the oceans near both the North and South poles. Using the data they collect, we are able to see how over the course of roughly a year, the levels of fluorescence, also known as chlorophyll A, have changed in these regions. Fluorescence, things like algal blooms and phytoplankton, rise and fall based on the conditions of things like dissolved oxygen, temperature, nitrates, and salinity in the given areas. As everything is connected, we can use that interconnectivity to map out how much and when we'd see fluorescence in the future. So we'll move along from the abstract right over to the introduction. In Introductions to Oceanography by P. Webb, we look through all the ways in which the ocean can and does change, everything from currents to energy creating waves and lunar pulls. This book explores all the ways the ocean moves and changes depending on what it interacts with, like waves turning into half pipes when the energy at the top of the wave moves faster than that at the bottom. With the knowledge gained from reading this textbook, we compare it with the data retrieved from the arrays to see how things like dissolved oxygen, temperature, nitrates, and salinity affect the growth rate of fluorescence in the water. Chlorophyll A is a scientific name for fluorescence, which is more commonly known as things like algal blooms or phytoplankton. These creatures have been found to flourish in specific conditions such as raises in temperature, as well as they usually means an increase in sunlight that is needed to complete photosynthesis, the process of turning sunlight into food and in the chlorophyll. From there, we're going to move on to the method. So the method we use in this is in the accompanying chart. You'll see the changes in the amount of fluorescence in 3 locations that make up the near polar zones. Over the course of roughly a year, the data shows that all 3 areas seem to maintain, for the most part, a relatively low amount of fluorescence for most of the year, except for the spike in the Irminger Sea array that is in the North Atlantic Sea. This array is located off the tip of Greenland and has moorings in the Imager Sea Array support sensors for measuring the air-sea fluxes of heat, moisture, and momentum, and physical, biological, and chemical properties throughout the water column. That is from the Ocean Observatory Initiative's site. Another array is the Station Papa array, that is the location off the coast of Alaska. These collect information on ocean acidification, the fishery health in the area, and the eddy variables. The final array in this group is no longer in use, but it was the Southern Ocean Array off the coast of Argentina, focusing on the CO2 sequences, temperatures of currents, and the water formations. The variation in placements in the array allowed them to have varying results in chlorophyll as a product. So in this chart you can see the rates in which the fluorescents show up over the course of roughly a year. In the blue you have the Imager Sea Array, in the gold you have the Station Papa Array, and in the green you have the South Pacific Array. And as you can see, the Imager Sea Array has a spike between April and July, which shows on the chart there, and then you have the Station Papa Array, relatively straightforward. It does have minor fluctuations along the way with a bit of scattering in near April, and then you have the Southern Ocean Array, which just tends to be a straight line right across. So the results of that would be, based on the included graphs, figure 3, we can see the results from the collected data as to how the concentrations of chlorophyll A changes in the different environments. Since chlorophyll A uses the process of photosynthesis, converting sunlight into food and energy, its growth is related to the seasons. In the chart we see that there is a spike in fluorescence between April and July at the Imaging Sea Array. This is likely due to the change of season. When winter turns to spring, the ice melts, creating higher levels of nitrates and lower salinity in the ocean near the masses. With an increase in nutrients from the nitrates, it feeds the following spike in fluorescence that grow with the sunlight brought in the late spring and early summer. The current also plays a part as they push the warmer waters up from the equator towards this area. We only see minor spikes from the Station Papa Array as the location sees a different form of climates, as the Alaskan coast is generally colder waters and sunlight for only half the year. This lack of warmth, paired with the sunlight being either always available or rarely available, causes less ideal growth area for fluorescence. The last array, the Southern Ocean Array, sees no variation to the amount of fluorescence found in the water. It's likely due to the cold water currents that are pushed up from Antarctica. With cold water that is consistent, they don't get a chance to grow in a large amount or see spikes like that of warmer waters. Over in figure 1 you can see I did map out where the 3 arrays exist. You have the Station Papa Array over here off the coast of Alaska, the Imaging Array over here off the tip of Greenland, and then the previous location of the Southern Ocean Array down here near Argentina. So in conclusion, we feed our plants in order to help them grow bigger, but only some of that nutrients gets absorbed. The rest is rinsed away in runoff from the rain or in melting snow, since runoff is a contributor to increasing nitrates in the ocean, and those help feed the fluorescents to help them grow. With that in mind, we can assume that the closer to the land the array is, the greater the amount of chlorophyll A it will have. Along the same thoughts, a warmer environment with lots of sunlight would also show an increase, as they need the light to perform photosynthesis. Given that on average we hear about Florida having a red tide, which is a huge population of algal blooms, that those would be ideal conditions. Warm water, lots of sunlight, humanity feeding it nitrates, and a warm current to produce the best place to see consistent fluorescent spikes. But it also leaves room for new questions, like is too much sunlight a bad thing? If it receives 24-hour light, will they still thrive? How hot is too hot for them to live? Thank you for viewing my research poster today.